Alright, for this activity, we're going to work on the temperature control lab activity, and the project, I should say. Let's briefly just go over an overview of what the project is and what it entails. I think having a big picture helps us before we start. So I just have on OneNote just a couple of notes about the project. And actually, let's just go to the course website while we're at it too. So, let's open up my internet browser, actually I have a link. Either way, so we have the course map, and let's just go to the course overview, and we can see kind of the outline of the course, at least as it stands today. Some things I just want to point out real quick, though, is we have this portion that was kind of the first test right here, and then kind of the second test as far as getting into PID control and all that. Now as we pick up this activity, we're kind of looking at integrating our models and looking at controller performance. We're kind of looking at the big picture, how everything is coming together now. So that's the purpose of this assignment, is to bring together first principles models and other models that we've discussed before, and to discuss how we put them together. All right, put that drawing away. So our objective in this whole three-segment project is to derive first principles models and compare them with increasingly sophisticated empirical models. We'll look at the accuracy and discuss which is more accurate and why. And then finally, we'll control based on PID, based on a PID, and look at the performance there. And the fun part is we'll do this not just with one, but two of our heaters. We'll be using both of them at the same time. The general pattern will be the first lesson will be applying a principle with one heater, and then it'll set you to work doing it with two heaters. Some questions to keep in mind as we do this are why we use the temperature control lab in general. So just think about why we're doing this. What are we supposed to be seeing with each of these activities, as well as looking at these variables we've discussed so much in the past. Other things to think about as we do these things are the question of if radiative heat transfer is significant, especially since it's a nonlinear quantity. Is the heater temperature a response first order or second order? What disturbances affect the system? What first principles parameters are uncertain that could be adjusted to fit the data? And what controller tuning parameters are the best? And finally, what criteria do you quantify as having good performance? How do you know good performance? So here's an overview of the objectives of the whole project. We'll derive a first principles model, a nonlinear first principles model. We'll look at NEFO-PDT and we'll compare them. Then we'll go to two heaters and do something similar, deriving a nonlinear transient model for two heaters. For estimation and regression, we'll fit NEFO-PDT and an SO-PDT, and we'll optimize our physics-based model, compare with a linearized model, and we'll discuss briefly moving horizon estimation. With two heaters, we'll fit parameters to the physics-based model based on a step test with two heaters, and we'll compare our first-order and second-order physics-based models. Finally, for temperature control, we'll look at tuning a PID controller, and we'll comment on characteristics of that control, and we'll move on to two heaters, and design interacting PID controllers. We'll tune them from constants, we'll do a step change and improve that tuning even more. So I just wanted to get a brief overview of what the big picture is we're doing with this. So the objective of this first part is to drive a nonlinear transient model and fit first-order linear data or second-order system. So we're familiar with the temperature control lab now, but we're going to look at the physical characteristics. For example, the mass of the fins in the heat sink is about 4 grams. It receives 1 watt of power at 100% power, and that's convenient for our numerical analysis. Steel has a heat capacity of 500 joules per kilogram, and then per degree Kelvin. The surface area is about 12 square centimeters, and the heat transfer coefficient for stagnant air, actually quiescent, I love that word, is about 10 watts per meter squared, and again, per degree Kelvin. So we have some other useful characteristics right here. We could make this more accurate when we talk about initial temperature and ambient temperature. We could take the temperature at time 0, which might be something cool. We also have heater power, quantities we've also talked about. Surface area, you'll notice it's in square meters here, so we have consistency. Same thing with mass, it's now in kilograms rather than grams. and then we have a conduction time constant. So we're going to first look at an energy balance. This should be pretty similar to what you've seen in heat and mass transfer courses. We have mass times the heat capacity, in this case of our heater, times the change in temperature over time, is equal to the energy in minus the energy out plus Q, the amount of heat that's coming into the system. If we were to expand these terms out, then we have two ways that heat is going in or out. We have first a lumped sum convection conduction going on between the heater and the surrounding surfaces. And then we have a radiation term as well. And then we have the alpha Q, which is for the heat generated by the heater. Let's see, other things. So we have emissivity and Stefan-Boltzmann constant, or at least that is what the sigma is. And Q is now a percentage of heater output. That way we can be 0 to 100, and that alpha will help us convert that 0 to 100%. It will help convert that percentage into watts of power that are going into the system. So I actually already have this coded up. So let's discuss this line by line. And maybe I'll make it even just slightly bigger. And I'll move this over. Let's hide it. There we go. Went too far down now. Oh, that hit all the code. I guess let's output below. That's good enough. So first thing to do, it's always safe to do, is to hit clear all, close all, CLC. That will clear all our variables, close anything we have running, and it will clear a command window. It will slow it down slightly if you were to do something where you're trying to optimize for performance, but that's just fine. We actually don't need to save this at test.m. That's a vestige of times where we were using actual MATLAB scripts versus these live scripts. So that's one nice advantage of what we're doing right now. All right, the next step we're going to do is the number of time points. We're going to go over 10 minutes, so we're going to have time points for 10 minutes and then one extra one to make it a full, just round it out. We're going to create an array for what our heater setting is any given point in time, and then from 2 minutes to 6 minutes, we'll set the heater to 70. This is going to be our temperature 1 in Kelvin, and then we're going to set it to our initial condition. We're assuming that the initial temperature is 23 degrees. Finally, we're going to store our time in this time vector. Then for our loop, we'll go ahead and we'll first simulate what we think will happen. We're going to integrate with ODE23 this heat function, which I'll scroll down to in just a moment. That heat function takes temperature, and then it takes x, which is our integrated arguments. And then qi is an input to the function. And it will integrate from time I to time I plus 1. And then we also have our temperature right here. So let's look at our heat function really quick. So our heat function has ambient temperature, U, which is that lumped sum parameter for heat transfer, M, mass of the heater, Cp, heat capacity of the heater, surface area, alpha, which is that conversion from it's that gain, right? So it's from percentage heater to the watts there going into the system. We have the epsilon, which is the emissivity, and the sigma, which is a Stefan-Boltzmann constant. So the first thing we do is we unpack the temperature. That's what we do right here. The temperature comes in as x in this array. We unpack it, and then dt, the rate of change of temperature, is equal to 1 over mass times heat capacity, and that's so that we have everything in the form. If we think of this equation right here, we want everything on the right-hand side and only this differential term, if you'll remember from a bit ago when we were doing these somewhat often. So that quantity times, first, the lumped sum convection conduction, or lumped parameter, I should say. Then we have radiation, and then we have the heat coming into the system. So we're going to go ahead, we're going to first run this portion right here. We're going to run this step test and see how the heater responds. And then we'll plot our results. So I'll go ahead, get ready for our output, and I'll go ahead and hit run and see you on the other side. I'm pause real quick. You can actually see it came out immediately, actually. I forgot that we're simulating the heater first, so we're not actually waiting for the heater. So the first thing that happens, it turns on at 2, off at 6, and we're going 100%. You can see the FOPDT come. Actually, this isn't the FOPDT. This kind of looks like one at first. This is the physical model of what's going to happen. Heat's going to increase. You can see it slowly tapering off as this is a nonlinear process. And then once the heater turns off, it slowly dissipates that heat to the system and doesn't have heat coming in. And so it's eventually going to return to the ambient temperature in a nonlinear manner. Then what happens is we're going to move on to the Arduino code while it's actually running right now. So what happened is first we created another array, this time for storage of temperatures. We connect to the temperature control lab, and we start our timer. Then we're going to set lab.q1 equal to that point, q1, record the temperature, and then pause for 1 second. Now that will be 1 full second from the time it hits this line to the next point. So it'll actually be just a bit off. And that's too bad. Let's actually, it's already heating up. So we'll just have to keep that in mind. These times won't be right on. So I'm actually going to pause it. And we're going to fix this. We're going to stop. Go ahead and fix this. But I'm going to say there's 2 ways we could do this. Number 1 is we could just pause for a full second, and then we just want to record that time. If these points are less frequent, we're still going to have the timing right. Actually, this would be off as well. Perfect. So if that's the case, what we'll do is this. We'll say pause for 1 minus, and then we're going to use mod, which is going to give us the remainder of the difference between talk, which is our current time, and 1. So the remainder will be some fraction of a second. 1 minus that fraction of a second should give us how much time until we hit 1 again. And then the final thing I'm going to do is I'm going to create another array similar to this one. Control C, Control V. This is going to be time underscore TCLab. It's going to be equal to zeros. So at each point, we record the temperature, we set the heater, and we'll do it just at the very beginning. So we'll say time underscore TCLab is equal to talk. Time underscore TCLab I. We need to set that specific instance. I'm going to come down here then real quick and say lab.off because I realized I left it. Yep, because I left it on. Let's see, lab.t1. What's our temperature at? 24? Okay, we're still good because it hadn't turned on, and I'm in Texas right now, so it's hot. So we'll go ahead and we'll run it for real this time. And now we'll see on the other side what the real results. You'll notice we're going to display in blue what the energy balance said will happen, and then our results from our TCLab. Alright, here we have our results. We can call this good pretty quick. Let me just note 2 things. And the blue line is our physics-based model, and the red dots are our measurements. 2 things I notice are first that the physics-based model doesn't take into account dead time, and so it starts right as soon as the heater turns on, whereas there's a gradual warm-up period before the heater starts working right away. The other thing is that we seem to be heating up much higher than the physical model anticipated. It looks like we get up to about just over 60 degrees, and we cool down a little bit slower. But not too much. It seems to be a similar shape, just offset by height. So the 2 observations, we'll look at doing it with 2 heaters in the next activity.